In this video, we're going to talk about the theoretical part of Thevenins and Nortons. And on our succeeding videos, we're going to apply these theories to some examples. Let's say we have a linear circuit. So this can be a circuit containing a single source, a circuit that only has one loop, or a circuit that has several loops and several sources. And from that circuit, let's say there are two terminals coming out of that linear circuit. Now, if we look at inside the linear circuit from the open terminals A and B, uh, what we actually see is a simple circuit that looks like this, which is a voltage source that is in series with an impedance. So the circuit on the right is what we call the Thevenin's equivalent of the linear circuit with respect to the open terminals A and B. The question now is, what is this VTH and ZTH? Now for VTH, this is the voltage when we measure or compute for the voltage across the open terminals. So let's say we call that the voltage V sub OC. Once we measure it or compute for that, that will be our VTH. For VTH, this depends on the condition of the circuit, and this is in general impedance across the open terminals if the independent sources inside the linear circuits or the linear circuit is disabled. When we say disable the independent sources, that means that for a voltage source, we need to short the terminals. And for a current source, we need to open the terminals. There are actually three cases. Uh, so if the linear circuit contains purely independent sources, getting ZTH would fall under what is called case 1, which is really just simplification of the circuit through the application of series parallel elements, um, provided there are no dependent sources. If the linear circuit contains dependent sources, we could apply what is called the process for case 2, which is again we turn off the independent sources inside the linear circuit, provided we leave behind the dependent sources, and then we apply a test voltage or a test current, and then determine the resulting current that will come out of the test voltage if we use a test voltage, or the voltage across the test current if we use the test current. And once we get the test voltages and the test currents, we can then apply this formula to get our Z sub TH. Now let's say we have a linear circuit, and on the uh, terminals there is an element connected, or another network is connected across these terminals. We could still determine the Thevenin's equivalent of that linear circuit by first isolating the element or the network that is connected to the terminals, and determine V sub th and Z sub th. And then after getting these parameters, BTH and CTH, we can then proceed by reconnecting the disconnected element or network and proceed to determine whatever parameters that we need to determine. Now let's go to Norton's theorem. Again, let's say we have a linear circuit and connected from that linear circuit are two terminals. Now looking at the open terminals again, what we see is actually a circuit that looks like the one on the right side. So it is a current source that is in parallel with an impedance. Um, this parallel combination therefore represents the linear circuit with respect to the open terminals. So the question now is, how do we get the current I sub n and Z sub n? Now for I sub n, uh, to get this, we apply a short across the open terminals A and B, and then measure or compute for the short circuit current that flows from A to B, so we call it I sub C, and that becomes our I sub n. Now for Z sub n, this is actually the same as C sub th, and we can determine it again as discussed previously using the cases that we have discussed a while ago. So for Z sub n, we could compute for this same as what we have explained in determining Z sub th. Now there is actually another case in determining Z sub th. Now we know for a fact that a linear circuit with respect to some open terminals A, B has a Thevenins equivalent, and also it has a Norton's equivalent. Now this means that these two circuits, the Thevenins equivalent and the Norton's equivalent, are actually equivalent circuits for the original circuit. What this means is that we could uh, say compute for the voltage across here. Say this is the open circuit voltage on the Norton's equivalent, and let's say we also compute for the voltage here across A and B of the Thevenin's equivalent. These voltages should be equal, and based on the Norton's equivalent, we can say that this voltage should be equals to um, I sub n Zn, and here this should be equals to V sub th. Okay, now this suggests that um, VTH is actually equals to I sub n times Z sub n, which is equals to I sub n times ZTH, since Z sub n and ZTH are the same. Thus, from these equations, we can actually say that I sub n is equals to VTH over Z sub th, or equals to the open circuit voltage V sub OC divided by ZTH. Also, we could say that ZTH can be extracted from the Thevenin's voltage divided by the Norton's current. So this is another way of computing for Z sub th. That is, We compute for the Thevenins voltage and the Norton's current, and the ratio of the two will give us Z sub Th or Z sub n. Thus, to summarize, we have a third case for determining Z sub n or Z sub Th, and that is getting V sub Th and I sub n. Um, so that means applying the Thevenin's theorem and the Norton's theorem to determine the C sub Th or C sub n. Thank you.